Computational fluid dynamics is a field of study that deals with the numerical simulation of fluid flows, using mathematical models and algorithms to predict and visualize the behavior of fluids. CFD has applications in a wide range of fields, including aerospace, automotive engineering, and more. CFD has become an important tool for engineers and researchers, enabling them to study complex fluid dynamics phenomena that are difficult or impossible to study experimentally. CFD simulations can be used to optimize designs, reduce costs, and improve the performance of devices that involve fluid flows. CFD simulations typically involve three main stages, namely pre-processing, solution, and post-processing. Pre-processing. This stage involves preparing the simulation domain, defining the fluid and solid regions, specifying the boundary conditions, and meshing the domain. The steps involved in pre-processing are geometry definition, creating or importing the CAD or the computer-aided design model of the system to be simulated. Next, domain creation, defining the region to be simulated, including the fluid and solid regions and the boundary conditions. Third, mesh generation, dividing the domain into a set of discrete cells, typically using structured or unstructured meshing techniques. And lastly, boundary conditions, defining the properties of the fluid and solid regions and their interactions with the surroundings. Solution. In this stage, the governing equations are solved numerically using a CFD solver. The steps involved in the solution stage are solver setup, setting up the solver and selecting the appropriate numerical method and solver settings. Next, solution, running the simulation and solving the governing equations for the fluid and solid regions. Third, convergence criteria, setting the convergence criteria for the solver and monitoring the convergence of the solution to ensure accuracy. And lastly, post-processing, exporting the results of the simulation for further analysis and visualization. Post-processing. This stage involves analyzing and visualizing the results of the simulation. The steps involved in post-processing are data extraction, extracting relevant data from the simulation results, such as velocity, pressure, and temperature. Data analysis, analyzing the simulation results to gain insights into the behavior of the system and identify areas for improvement. And lastly, visualization, creating visualizations of the simulation results, such as contour plots, vector plots, and animations to aid in understanding and communicating the results. Turbulence is a complex and chaotic flow phenomenon that occurs in fluid flows when the fluid motion becomes highly irregular and unpredictable. In turbulent flows, there are small-scale eddies and vortices that interact with each other, leading to a highly irregular and random motion. This makes it difficult to predict the behavior of the fluid flow accurately. Turbulence models are mathematical models that are used in computational fluid dynamics simulations to approximate the effects of turbulence on the fluid flow. These models attempt to capture the effects of turbulence on the mean flow behavior by representing the small-scale turbulence phenomena in terms of macroscopic quantities that can be more easily computed. There are various types of turbulence models, ranging from simple algebraic models to more complex models based on partial differential equations. Turbulence modeling is an active area of research in CFD, with ongoing efforts to improve the accuracy and efficiency of turbulence models for different types of flows and applications. Some of the commonly used turbulence models include: first, Reynolds average Navier-Stokes or RANS models. These models solve the time average equations of motion and are widely used for engineering applications. Second, large eddy simulation or LESS models. These models resolve the largest turbulent eddies and model the smaller eddies using subgrid scale models. Third, direct numerical simulations or DNS models. These models resolve all the scales of turbulence and are the most accurate but also the most computationally expensive. Fourth, K-epsilon model. The K-epsilon model is a two-equation turbulence model that solves two transport equations for the turbulent kinetic energy, or K, and the rate of dissipation of kinetic energy, or epsilon. The K-epsilon model assumes that the turbulence is isotropic and homogeneous and that the turbulence viscosity is proportional to the local value of K and epsilon. Fifth, K-omega model. The K-omega model is another two-equation turbulence model that is an improvement over the K-epsilon model in predicting near-wall turbulence. The K-omega model solves two transport equations for the turbulent kinetic energy, or K, and the specific dissipation rate, or omega. The model assumes that the turbulence viscosity is proportional to the local value of omega and that the eddy viscosity is limited in the viscous sublayer. Sixth, Spallart-Almaraz model. The Spallart-Almaraz model is a one-equation turbulence model that is computationally efficient and accurate for a wide range of turbulent flows. It solves a transport equation for the turbulent viscosity, which is a function of a single variable called the turbulence intensity. The model assumes that the turbulence is anisotropic and that the turbulence viscosity is proportional to the local value of Nu. Numerous fields of study have certainly used computational fluid dynamics due to its capabilities to simulate the behavior of fluid flows. One particular example of its application is the study of aerodynamic performance of an aircraft in various velocities and angle of attack. In the study entitled Biomimetic Wing Morphing of Unmanned Aerial Vehicle or UAV Platform for Rapid and Precise Post-Disaster Assessment, computational fluid dynamics served a vital part in determining the aerodynamic performance of an unmanned aerial vehicle design configuration. The study intends to determine the best suitable morphing wing configuration for a commercial UAV design for its loiter and dash flight phases. In this case, the lift-to-drag ratio of the various wing configuration needs to be determined, which can be done through the lift and drag force calculation of the simulation. In the study, the ANSYS Fluent software will be used for CFD. Before initializing the ANSYS Fluent simulation, the CAD design of the UAV must first be prepared in SolidWorks. Although ANSYS also offers CAD design capabilities, a complex design such as UAV is more efficient and easier to be designed through SolidWorks. Once the CAD design is ready, the file must be saved as a step file since the import function for geometry in ANSYS only accepts such file format. Once this is done, then the ANSYS Workbench software may now be utilized. For a guided flow of the pre-processing of the CFD simulation, the predetermined analysis systems set by ANSYS in the Toolbox section may be used. The fluid flow or Fluent system will be used for this particular simulation. Simply click the fluid flow or the Fluent system and drag it to the workspace for the project schematic. As can be seen, the simulation undergoes at least 6 phases, starting with geometry, mesh, setup, solution, and lastly, results. Let's begin with the geometry phase. To load the previously created UAV CAD design, right-click on Geometry. Then, hover the cursor to import geometry and click Browse. Look for the step file that is intended to be simulated. In this case, the telescopic wing configuration for cruise flight. We then right-click on Geometry again and click Edit Geometry in Design Modeler. Once the Design Modeler is initialized, the imported geometry was not generated yet. We then have to click on Generate Feature to load the UAAV body. The created design lies on the ZX plane, but we prefer the design to be situated on the XY plane for an easier lift and drag calculation setup. To rotate the body, we go to the Create tab, hover over Body Transformation, and then click Rotate. Click on the body that we want to rotate and click Apply. Next, click on ZX plane, then click on Axis Selection, then once again Apply. Notice that the UAV rotates towards the negative x-axis, but we want the plane to be facing towards the positive x-axis. We then set the angle to 90 degrees, then change the orientation of the axis selection using the arrows seen on the lower left and click Apply. To set this transformation, click Generate. Since we want to investigate the aerodynamic performance of the UAAV at various angles of attack, we set an input parameter for angle of attack. To do this, click on Create once again and click on Rotate in Body Transformation. Click on the telescopic cruise body as the body and XY plane for the axis selection, with the orientation arrow set towards the positive Z direction. Set the angle to 0 since it will be our base configuration. We then add a design parameter by clicking the box area beside the FD9 angle detail and rename the parameter name as AOA. Then, generate. This parameter will then enable us later on to have a parametric solution without having to set up the simulation for every angle of attack. After setting up the geometry configurations for the UAAV, we now have to set up an enclosure that will serve as the boundary for the fluid flow analysis, acting like a wind tunnel for the UAAV. Go to Tools, then click Enclosure. We then set up the dimensions for this enclosure. In this case, we'll have 0.25 meters, 0.15 meters, and 0.25 meters for the positive X, Y, and Z axis, respectively. Similar dimensions will be set for the negative axis, except for the negative X axis, which is set to 0.5 meters, which is larger than the dimension for the positive X axis, since we have to account for the streamlines of the flow after the air encounters the UAAV. Once the enclosure is created, we need to create the boolean to subtract the UAAV geometry from the enclosure. Go to Create, then click Boolean. Set the operation to subtract and identify the closure body as the target body and the UAAV body as the tool body. Then, generate. To lessen the computational time for the simulation, we can use the symmetry tool of the software, considering that the UAAV is symmetrical along the XY plane. Go to Tools, then Symmetry. Set the symmetry plane to be the XY plane, then Generate. After this, the geometry is now ready for meshing. Close the Design Modeler and go back to ANSYS Workbench.
For the second phase, double-click on Mesh to initialize the ANSYS Mesh software. Click Generate to prompt the automatic mesh of the design. Set the element size and max size to be 750 mm. Go to the Mesh tab, then add sizing. Let's first add edge sizing for the mesh. To do so, click on the edge selection figure at the toolbar section below the tabs. Click on the edges of concern, in this case, the outer edges of the wing, fuselage, and tail. Use the Control command to enable to click all the edges concerned. After doing so, click on Geometry, then Apply. Set the element size to 1 mm and set growth to 1.0 and capture curvature to Yes. After this, add face sizing. Go to the Mesh tab, then add sizing. Click on the face selection figure at the toolbar section. To select all the faces of the UAV, change the selection mode to Box Select. Then, create a box select containing the entire UAV. This will supposedly highlight the UAV faces. Click Apply in Geometry. Set element size to 115 mm and growth rate to 1.0. Also, set the capture curvature to Yes. Since we are aiming for a smooth fluid flow over the UAV, we will add an inflation. In the Mesh tab 0, click Inflation. Change the selection mode to Single Select once again. Then, click the enclosure. Apply it as geometry. For the boundary, change the selection mode to Box Select and the face selection figure. Select the entire UAV and click Boundary, then Apply. To apply the mesh configuration, click Generate. To check for the mesh quality, set the mesh metric to skewness and change smoothing to high. The target skewness is below 0.95. For instances that the maximum skewness is above this value, then we have to change the configuration of the mesh until it satisfies the mesh quality. Once the skewness of the mesh is satisfied, we have to name the boundaries of the enclosure. Set the selection mode to Single Select and Face Selection. Click on the inlet boundary and type N. The selection name dialog prompt will appear. Type Inlet, then OK. Now click on the outlet face and name it as Outlet. Click on the Symmetry wall and name it as Symmetry. Click on all the remaining enclosure faces and name it as Wall. Lastly, change the selection mode to Box Select and highlight the UAV. Name this selection as Plane. Once this is done, the meshing phase of the simulation is done. Close the mesh software and go back to Workbench. Right-click on Mesh and click Update. This will supposedly update the mesh of the geometry. Once this is done, proceed to Setup. The Fluent Launcher dialog box will pop up. Click on Double Precision and set the solver processes based on how many processors your computer have. To check the number of cores and logical processors, go to Task Manager and go to Performance tab. In the CPU section, the number of cores and logical processors can be seen on the bottom. For my case, I will set my solver processors to 10. As you can see on the mesh, the flow of the fluid can already be seen since we already set our inlet, outlet, symmetry, and wall faces. For this study, we set the general setup to pressure-based for the solver, absolute for the velocity formulation, and transient for the time. For the model, we set it to viscous and use the K-epsilon turbulence model. All the other configuration for the model is set as is. For the fluid and solid under the material setup, we shall use the base setup of air for fluid and aluminum for solid. We now then set the boundary conditions. Make sure that the inlet is set as velocity inlet, interior solid as interior, outlet as pressure outlet, plane as wall, symmetry as symmetry, and wall as wall. Now, we need to edit the inlet velocity. Click Edit under Inlet. For the velocity magnitude, click on the drop-down arrow and click on the New Input Parameter. Since the study intends to observe the behavior of the UAV at varying velocities, we have to set another design parameter for velocity. Set the name of the parameter to inlet underscore velocity and set velocity to 13.5 meters per second. Notice that the use as input parameter is checked. After this, click OK. Then apply and close. After the setup, the solution phase follows. Under Methods, set the scheme to coupled and the gradient to least square cell-based. Set all the other configurations to second order including the transient formulation. For this simulation, the data that needs to be extracted is the aerodynamic performance. In this case, we need to add lift and drag to the report definitions. Go to Report Definitions, click New, then Force Report, then Lift. Change name of the report to lift_force and report output type to lift force. Set the wall zone to plane and mark check the report file. Report plot and create output parameter. This helps us see the lift values during parametric solution. Click OK. Similar with lift, do the same thing with drag. Go to New, then Force Report, then Drag. Rename the report to drag_force and the output type to drag force. Set the wall zone to plane. Change the force vector to -1 under force vector since drag is along the negative x-axis for the setup. Then mark check the report file, report plot, and create output parameter. Click OK. Then close. Set solution initialization to hybrid initialization and initialize. Then proceed to run calculation. Set the number of time steps to 100 and time step size to 0.1 seconds. Then calculate. Once the simulation runs, the plots for scaled residuals, lift force, and drag force can be seen. Once all the time steps are done, the software will prompt that the calculation is complete. After the simulation, contours and animation can be extracted from the solution. For this study, since the lift-to-drag ratio is the main concern, we will then simply record the data for the lift force and the drag force. Going back to the ANSYS workbench, we can see the input and output parameters for the design. From this table, we can then run a parametric solution for the UAV design, with varying angles of attack and inlet velocity. For this particular study, we will run the simulation from the angle of attack of -6 to 12 degrees with an increment of 2 and an inlet velocity of 10 meters per second, 13.5 meters per second, and 17 meters per second. To do so, simply type the AOA and inlet velocity configuration on the last row of the table. Then click on Update All Design Points on the upper left corner to run the parametric solution. To monitor the progress, simply click Show Progress on the lower right section of the interface. Doing so enables us to simply wait for the results of the simulation without having to set up each design and parameter configuration.